Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 61st Project Euler problem. As always, I will link to the problem and my repo in the description. Let's dive in. Problem 61 is cyclical figurate numbers. Triangle, square, pentagonal, hexagonal, heptagonal, and octagonal numbers are all figurate, polygonal numbers and are generated by the following formulae. I'm not reading those. The ordered set of three 4-digit numbers, 8128, 2882, 8281, has three interesting properties. The set is cyclic in that the last two digits of each number is the first two digits of the next number, including the last number with the first. Each polygonal type, triangle, square, and pentagonal, is represented by a different number in the set. This is the only set of 4-digit numbers with this property. Find the sum of the only ordered set of 6 cyclic 4-digit numbers for which each polygonal type, triangle, square, pentagonal, hexagonal, heptagonal, and octagonal, is represented by a different number in the set. Okay. So, a while ago, there was another Project Euler problem, problem 45. I went and looked it up. That was similar. And that time it only had triangle, pentagonal, and hexagonal. But it's the same formulas and everything. So, I probably flipped back and forth too fast for you to be able to see that, but yeah. So now we have many more of these formula. I'm going to end up copying them over manually, I think. So, the first task is going to be finding a 4-digit number that is triagonal. And I've already pulled up my code from problem 45. Wonder if I can... Okay, I don't see a simple duplicate button, so... Okay, so I'm actually I'll go ahead and copy this part. And go ahead and grab the other formula as well. Okay. all of that now, do we? I'm going to call this S in instead. Ooh, heptagonal is also starting with an H. So we'll use the letter E. Not going to confuse myself at all with that one, I'm sure. Okay. Okay, so those are original formulas for taking a number in and finding the triangle, square, pentagonal, etc. numbers. However, what we are going to have is we are going to have a number, and we're going to want to find out if it is pentagonal, hexagonal, etc. So I'm going to copy this also to help myself remember what we're doing. And I already have, for pentagonal and hexagonal, these methods. I'm going to go ahead and copy over all of that. So is valid in, we're definitely going to keep. The struggle here is we need to find our other formulas. Let's see, so what I did here is I had a while true, and then I did a break. So what we need to do is quite a bit different from last time, but we do still need, like, this find in P, wherein I used the quadratic formula to figure out how to find an n given the pentagonal number. And the same here, but for hexagonal, those are going to remain the same. But the triangle, we need to come up with a few other such formulae. So, let's see. For I know, I can use Q here for square, and then S here for 7, and that might be less confusing. We'll find out. So for a triangle, if we have a number here, say x, that is equal to this, so this is going through and finding the algebra. So for the triangle formula, we're going to end up having x equals n plus 1 divided by 2, which is the same as 2x equals n squared plus n. That is not what I meant to type. So effectively x is equal to 1/2, I'm going to say 0.5 n squared plus 0.5 n. Multiple ways I could have approached that, I'm sure. And then now we have it in the form that we can use the quadratic formula to solve. It becomes, so b is 0.5 plus or minus square root of 0.5 squared minus, oh, c is 0 though, so never mind, that whole part gets ignored. Divided by 2a, which is also 0.5. And this translates to 1, so not divided by anything. .5 squared is 0.5 times 0.25, which is, or 0.5 times 0.5, which is 0.25. So 0.25. Oh, wait. I'm being dumb. So c is actually just negative x. This is our actual representation of the formula with x inside of it. And we will have x, and we're trying to find n. So we're just kind of pretending x is there. So negative 4ac, c is negative x, which means this turns positive. 4 times 0.5 times x all over 1. Again, in this case, it's 2 times 0.5, which is just 1. Yeah. So we should be able to simplify this somewhat. So 4 times 0.05 is 2. So this becomes 2x. This becomes 0.25. Again, I change it so that it is Okay, so that's the triangle formula. Square formula is way, way simpler. Because it is literally just x, the square root of x. Pentagonal and hexagonal I've already worked through. Heptagonal. Okay, so x equals times 5n minus 3. So 2x equals that. And then 0 equals 5n squared minus 3n minus 2x. So translating that into our little doohickey here, we get okay, come on. Negative b is 3 plus or minus I'm just going to go ahead and put it in that formula right immediately. Okay, b squared, which is 9, minus 4 times a, which is 5 times 2 times x. And then all over 2a, which is 10. I prefer having more parentheses around this guy. Okay, so I want to simplify this a little bit more. 4 times 5 is 20. 20 times 2 is 40. So it's actually 40 times x. Okay, not too bad. One more. Obviously, this is taking quite a bit of our time, but this is kind of what this is building a foundation that'll make the rest of this problem very easy. Hopefully. Okay. For octagonal, x is equal to 3n squared minus 2n. So 0 is equal to that minus x. Which is equal to, okay, negative b, so 2 plus or e minus b squared, so 4 minus 4ac. A is 3. C is negative x, so this becomes a plus symbol. And then all of that is 0.5. And then all of that is divided by 2a, which in this case is 6. Simplify this a little. 12 times x. Okay. We have all of our formula. Now we just gotta make these find in of all of the other of those 4 formula we just created. But again, luckily we have set ourselves up for success a bit here, in that we already have this is valid and we already have methods for 2 of these. So n of t is just this. I'm just going to switch that to x, and then I'm going to do the same for all of the other ones. No, never mind. I am changing my mind immediately. It does not actually make much difference. So forgot to properly create the formula. That's fine. Okay. And that's it. Can't help but feel like I can break these lines out. Now I can just say return is valid in N1, N2. Actually, now I can replace all these lines with just find valid in, and it's a small refactor right now, but it'll pay dividends as we continue working on these formulas. Okay, so n of q, which is what we're going with for the square, q for quad. Okay, so here it is actually a little bit different. We're going to hard code this to -1 because we know that that's wrong, or not a valid n. So if n is not valid, it'll work just fine. Okay, on to the 7. Find n s for s. A little bit weird to be using s for not a string, but that is just fine. And then we do for octagonal the same way. Okay. Okay, so now we have all of these little methods that will find out if we have a valid n for a particular number. So what we want to do, duplicate our print statements. Now we're actually getting started on the real problem. And how I want to approach this is I want to go through all 4-digit numbers, and if they are triangular, grab the last 2 digits and go through all 4 digits numbers that start with those 2 digits. And kind of so on and so forth, which is going to be a pretty deeply nested set of for loops. But let's see how quickly we go through it. It should be pretty quick. So we've got this here. And I'm going to use t for this first one. For t in range 1,000, 10,000, because we know. And then we're going to say if find n of t for t is greater than 0, which means we found one, or we find one that is valid, then we are going to see q is equal to last two of Q, and I am doing quite a lot in here, all in one move. I want to break this out and create a method out of it, I think, just so it's less confusing. What we're doing here is we are taking the previous number, breaking it into an array of string representations of each digit, and then starting with index 2, grab those digits. So in other words, grab the last two digits, and then we are going to join those two together into a string, and then we are going to convert it to an integer. So, and then actually I want to multiply by 100 because that's the first one. And then I'm going to say while Q is less than, oh, Q is always going to be less than Q times 10. Not what I wanted. And then end is just going to be start times 10. Love when my fingers work. It's so rare. Okay. And then this becomes a for loop. Okay, so you probably already see where I'm going with this. Now, I'm going to keep building out this pattern. If find in Q for Q is greater than 0. I'm trying to think of a way that's good for making this recursive or something, since there is quite a lot of duplicate code here. But I think I just have to keep going. And then after Q comes P. That's not how the alphabet works. P for P is greater than 0. Copy our start and end again. After P is H for hexagonal. exact same thing again, except this needs to be a P. Gotta make sure I change that every time. Which means that this needs to be an H. And that needs to be moved over. Okay, 2 more. S and O. For the last one, we actually want to do something different, which is check whether the last 2 digits of O are the first 2 digits of T. So how do we go about doing that? Well, we grab all of this. So this is going to be last 2, first 2, similar formula, except here we're doing this, and we end at index 2, and if last 2 is equal to first 2, is found equal to false. Is found is equal to true. I don't want to call it a set. I'm just going to say nums. Nums is equal to T, Q, P, H, S, O. And then we break. No semicolons. This is Python. And then here we say if is found. Why am I setting checking whether equals true? Break. And then we basically do this repeatedly. Okay, so O, S, H, P, Q, T. So I'm missing 1. There. So this is just so that we break completely out of the loop here. And then we break. 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 And then And what I'm going to do is say found nums. What's the actual question in this problem? Find the sum of the only ordered set, blah, blah, blah. Okay, so cool. And this, in theory, should just work. But let's see if that is accurate. Okay, so it probably is going to take a while because we're basically checking 100 different numbers. Let's see. 1, 2, 3, 4, 5, 6. Well, we're checking 100 different numbers to the power of 5. So this really might not work at all. But, oh, it did work. It took about half a minute. It found 5 concatenating primes. I ran the wrong file. Okay. When we run the correct file, we find out, oh, well, that's not a thing. Between instances of complex and int. Are we getting a negative number somewhere? Here's what I'm going to do, is I am going to say if type of n is complex, return false, and see if that fixes this problem. Seems to have. Because if I remember complex number properly, it means it has like an I in it, which is the square root of -1. Which means that it is not a valid integer n. So, let's see. Okay, so now it has taken a bit of time, which is just fine. Like I said, this might take a while, since it's going through like thousands and thousands of numbers. It might actually be faster now that I'm thinking of it, to approach this entirely differently. So, I'm approaching it as, let's find the number and then see if there's a valid n for that number, but the problem is I'm checking far too many numbers this way. So instead, I am going to approach this completely differently. I am going to leave all of my notes here, but basically, instead of trying to find n, I'm going to start with an n and find the t. And here is how to do that. Yeah, we're just going to throw away all of that code. Okay, I'm actually feeling like this is the wrong way to go about this, so I'm going to go ahead and just make the new methods and leave these in here, just because that is what I feel like doing. So find t of n for n is this guy. Find q n is just n squared. Now, I feel like these really don't actually need to be their own equations, but maybe things will be more complex at some point. Okay, so as I sort of work through this, my basic plan here is to go through, find all of these numbers, and then like have all, let's see, it's 9,000. Find all 9,000 of these 4-digit numbers, I guess. Or, oof. This might not work the way I hope it will. But basically I'm gonna go try to find all of the 10-digit numbers, or 4-digit numbers, excuse me. And then go through all of those numbers that we know are triagonal and use finding inside of an ordered list instead of this nonsense that I was doing here, which has been going for about 7 minutes and is still not done. So clearly not an ideal approach. Okay. Just double checking some of my formulas here real quick. Okay. So now, instead of all of this, which I'm just going to comment out, I am going to say n equals 1, and then while n is less than 10, actually, less than 10,000 might not be good enough. I'm trying to switch back to the problem real quick, because here we've got this 3,000. Oh, I see. 44, 91, 127. Okay. That should be fine then. So, while t is less than 10,000, n plus equals 1. So I think all of these start with a 1. Yes, for all of these, n of 1 is just 1. Or maybe it's n of 0, that's just 1. No, it's n of 1. So n plus equals 1. T equals this. And then if t is greater than 999 and t less than 10,000, let's see. I'm gonna go ahead and make a bunch of different. So we got t. P for pentagonal. These could be dictionaries, but I think that it doesn't make sense for them to be. S or H for hexagonal. S for seven-gonal, which is heptagonal. And then O for octagonal. So, I am operating off of the t's, primarily. And then I'm going to throw another function in here that is def. Actually, I'm not going to do that yet. So basically what I'm saying is if t is a 4-digit number, then I want to add it to t and s. And I want to find all the others. Actually, I could just do this multiple times to fill up each of these arrays. Yeah, I'm gonna go ahead and do that. If I can think of a way to generalize it. Okay, so I believe that I am allowed to create a function that takes in a function. So def find all fours, and I am going to take in a func. Yes, this will work. And then in here, I'm going to say n equal to 1. X is equal to func of n. And then if, or rather, while x is less than 10,000, x equals 1, x equals func n, and then if x is, I could do this a different way. I could just say length of string of x is equal to 4. Nums.append x. Actually, I'm just going to go ahead and call this fours to make it a little bit more clear. And then all this does is it returns fours. Okay, so find all fours for find t for n, and then same thing repeatedly. So 3, 4, 5, 6, 7, 8. Q, Q. P for pentagonal. H for hexagonal. S for heptagonal. And finally O for octagonal. Okay, so now for T in T and S, we want to do this same thing So first two we're not actually going to use for a while. Okay, so this this and even this, it'll be just as easy to deal with this as strings. And actually all of these as well. Obviously, I'm going to go ahead and change all of that again. Actually, what if I just did this? Okay. So now we're dealing with strings. And then we are going to want to use a list comprehension to find any cues starting with last two for each of those. Get last two and repeat. Find any p's starting with last two and then repeat. Okay, so this should be a significantly reduced set of numbers. I'm actually going to go ahead and take a bit of a break at this point, but I'll be right back from your perspective. And I'm back. Okay, so list comprehension, find any cues starting with the last two. I know that this can be done. And that's about where I am right now. I'm just going to call this cues. And this is going to be a list comprehension where I am going to say S X for X in, or I'm going to say X if F X dot I do not know if there is a starts with here. X for X in QNs if X dot starts with last two. And then for Q in Qs, Qs just going to repeat. Except after Q comes P. So for P in P's, now this H's. H is S's. Ooh, that feels like a bad variable name. But it'll probably be fine. The computer does not give a does not care. So it'll be all right. And then here at the very bottom, we say if, or actually we're just going to do this again, but this time, oh right, we gotta first do our for loop. For O in O's, last two is that, and then if first two equals last two, and I'm actually going to convert both of them to ints for this comparison, just in case there's some weirdness about string comparison. Then we can do our is found thing again, I think. Is found becomes true. Nums is equal to the exact same thing as I had it down here, although it seems like I've managed to make a somewhat less nested loop here, which is great. And then I want to break out of this loop, and then I want to break out of this loop if is found break. Okay, so break out of O, S, H, P, Q, T. Okay. And then we can still use the same print statement. So again, this is a lot of very nested loops, which isn't necessarily the best way of doing this, I feel like, but this should be a lot faster than our previous attempt Oh good, I added in all of the breakpoints. Okay, well, saying nothing at all in 100 or a tenth of a second sure is a way. Oh, this is now a string. So I can literally just do this here. Whoops. I don't think this is why we're not finding an answer, but just to make our code somewhat better. I'm just gonna run it again just in case. Okay, same result. I'm gonna go ahead and print TNs here. Okay, so we are finding numbers. And let's see, what was the one in the problem? 8128. 8128 is here. I don't think printing these other arrays will help me. So I'm going to go ahead and print QS here. And that'll print out a whole bunch of lines, but I'm just gonna print T. That way I have some idea what number we're looking for. So for 70, I see the problem now. Or at least I see a problem. Scrolling back up. Okay, too far. Going back to our example. Okay, so 2, 4, or 2, 3, 4, 5. And then I bet just for this one, it is like adding 6, so the next number is 21. Okay. I have a feeling something is wrong with our Q's, because I kind of doubt that 7002 and 7003 are both squares. No, not ever. Just bring up the calculator, Google. Thanks. I'm gonna say 9102. Okay, clicked the wrong button first, didn't I? Yeah, that's not a correct number. So how is this happening? Let's see, so just for n2, I am going to print out x. Leave off that. Zero. Ah, I know what's going on here. That's how that should work. Okay, so now we got 3, 4, 5, 6, 7, 8. Oh. I've got to convert these to integers, I think. Okay, now let's see. Nope. 3, 4, 5, 6, 7, 8, though. Oh, well, doing it there isn't going to do anything for me. Okay, so this is always going to be an integer. This is always going to be an integer. But for all of these where we're dividing by 2, which I guess was only 5 and 7 left. Okay. so far things appear to be working. Now, let's go ahead and print the Q's. Okay, that is a much reduced list, so now I'm convinced that our things are actually working the way I expect them to as far as that goes. Okay. Just gonna see how far we do get. And I'm going to say if length of QS, I don't know why I have these parentheses here, is greater than 0, then do these two prints. And I am going to similarly just so I can kind of see what is going on. Because clearly something is not correct here. We're going through super fast, so that's a good sign. Okay. Okay, so got 4 of them. Oh, but not really, do I? Okay, so if this is triangle, 4, 5, 6, 7, 8. So fell down at the end of there. Everything appears to be working, and it's just not finding anything meeting this condition. Rereading the problem. Ah, I was assuming that these numbers would be in order. They are not. They are not in order, so... Oh boy. I'm still going to start with T because the cyclical nature means that no matter which one you pick to start with, you will loop around to the beginning. So here's what we're gonna do next. We have a working algorithm here, somewhat. But instead of just this, we want to find all of them. So basically, but in a reduced fashion. So we start with the t's in T and S. And then the next number could be any number in any of these lists. But then the next number, if the next number is found here, say, it will not be in this list, and it can only be in 2, 3, 4 of these lists. So writing that all out manually, we're not doing that. We're going to do a recursive function. And I know that I can do Python args. Blah, blah, blah. So we want to do that. Find cyclic star and I'm going to say x's. And then for x's and xs's, x's is actually I want last two. Equals x for x in x's spending a little bit too much time on the variable names here, but that's okay. Result equals an array. X and S. We get all of the ones that start with our last two. And then for num and nums, 2 is equal to num less 2. Double checking myself. Yeah, so this comes in as a list. Okay, so what I want to do is call the cyclical function again, sending it last 2, and Python remove index from list. Not quite what I want. That is what I want. Hey, well, sort of. Close enough. I don't know for sure that this will work the way I want it to. But basically, seems like a waste of time, actually, now that I thought about it. So, if the length of new x NSS equals 0, meaning we're finding the last one. Or actually, let me do this a different way. Yeah. Another. If first two unnecessary parentheses equals last two, and length of x NSS equals 0, return empty. So I'm making a new last two every time, but I'm passing down the exact same first two. And then I'm going to say if length of result equals 0, how am I going to do this? So, result equals find cyclically. So, at the very bottom, we're going to return an empty array. And then we're going to do result dot append num Okay, this is not quite right, I think. I'm trying to think through how I'm going to do this. So find cyclically, at the very end, we want to return this. this doesn't seem correct. Okay, so what if here I return true? This is kind of a wonky way of doing this, I feel like, but Python will let me, I think. If is found, result dot append num. Okay, so this is going to be either true or non-empty list. And I think that an empty list is falsy. Let's double check myself. Python empty list falsy. Okay. Looks like that is an accurate assumption to be making. Break. Break. Okay, so if this works the way I think it should, which is not a guarantee of anything, we're going to come in with a list of all of these arrays, and then reduce that list etc. So now instead of all of these things, okay. All of these things. I'm moving this up to live with its other functions that I'm now not going to be using. Well, I'll be using some of them. Qns, Pns, Hns, Sns, Owens. And then if nums dots, length of nums equals... Okay, so this is really going to only be 1, 2, 3, 4, 5. But we're going to know that T is part of the list. I'm going to change this to false. Because... Okay, so if result... if type of result is not list, result equals that. There we go. This should be fine. Now I'll just have it be this here. So it'll return an empty list sometimes. And that's okay. But if it ever returns a list of 5 numbers, nums.append t break. Okay. And then we still have this. Let's see how well this works. Not very. Okay, so it's going to interpret this as a tuple. So I'm just gonna cheat. There. Now it's a list. How can it not be in the list? Like, how is that even possible? Okay. 1, 0, 2, 4. So obviously not this first one. Or the second one. What if I do it this way? Same error. So it's clearly working for some of these since we are printing out so much. But it is confusing to me why it wouldn't work for all of them. I might not be doing recursion quite correctly. No, it's this. I need to be able to copy this list, not set it equal to. Python copy list. Okay, let's see if that removes that error. Okay. Not great. That's gonna remove. Let's go ahead and remove this print. Okay, so now we're getting to this print statement, and it's saying, you can't add together integers and strings. So if we do it there, okay. So I feel like this did not sort it the way we need it to be sorted, but let's see if we can get there. So 2882, looking for the one that starts with 82, 8256, 5625, 2512, 1281, 8128. So this looks like a correct answer. And it is. All right. So that problem did have a difficulty rating of 20%, so I'm not sure why I thought I could get it done as quickly as I wanted to. But all's well that ends well. I think this is my first time doing recursion in Python, so I'm glad that the only reason it didn't work is because I'd not copied the list over correctly. But in any case, we got the correct result, and we got it in like 2/100ths of a second, which is incredible. So, going through our algorithm again, there's a lot of junk in here now that I really don't need, but I'm going to leave. I'm gonna leave it anyway. Or actually, I'm just going to create polygonals.py, and I am going to copy all of this. And while I'm at it, all this nonsense. So, now I could honestly import this file whenever I need to use these functions again. If I ever need to use these functions again. And now I can safely delete all of this. I don't think I actually need to save this code. I'm gonna go ahead and delete all of this, though. There. Cleaner. And actually... I'm gonna go ahead and do this. Because those are all in polygonals. And then from polygonals import everything. There. So that might be a little bit confusing for people who aren't used to like object-oriented programming, perhaps. But now this file is a lot smaller, and all we're doing is just finding all 4-digit values for each shape, I guess, and then for just starting arbitrarily with the t's, it could be with any of the numbers. We find the last two, and then we look for a list of cyclical numbers starting with those last two, and if we find 5 of them, we append our t and we break. So yeah, and of course we just print it out. I'm doing quite a lot of relatively complex list conversions lately, so if you would like more explanation of those, please drop me a comment and let me know. Otherwise, I will see you in the next one.